Welcome back to the Ping AI podcast, everyone. I'm Ping, your host, and today we're tackling one of the most exciting frontiers in science and energy, fusion reactors. Joining me once again is Claude from Anthropic. Claude, last time we chatted about this, we covered a ton, but your feedback has us refining it to make sure it flows like a real conversation. So let's keep it natural as we explore everything from the basics of fusion, its rich history, the cutting-edge science today, the profound implications for our world, future roadmaps, realistic timelines, and how AI is turbocharging the progress.
Definitely, Ping. Fusion's that elusive dream of unlimited clean energy. And with all the momentum building, it feels closer than ever. Why don't we start with the essentials? Can you break down what nuclear fusion really is and how it contrasts with the fission tech in our current nuclear plants?
Sure thing. Fusion happens when two lightweight atomic nuclei, usually isotopes of hydrogen such as deuterium and tritium, slam together with incredible force and merge into a heavier one, like helium. In that process, a tiny fraction of their mass converts straight into energy, pure E/mc² magic from Einstein. It's the powerhouse behind the sun and stars, generating heat and light on an astronomical level. Fission, which powers today's reactors, does the opposite. It splits heavy atoms like uranium, releasing energy but leaving behind nasty, long-lasting radioactive waste. With fusion, the main byproduct is helium, which is totally harmless and doesn't stick around as radiation. And the fuels? Deuterium is pulled from ordinary seawater. There's enough there to last humanity for billions of years, and tritium can be produced from lithium, which is abundant in the Earth's crust. It's a far cry from digging up rare uranium deposits that come with all sorts of geopolitical headaches.
That's a solid overview, but pulling it off here on Earth is no small feat because those nuclei are positively charged and repel each other fiercely. To make them fuse, you've got to heat things up to 100 or 200 million degrees Celsius, hotter than the sun's core, and squeeze the plasma, that superionized gas, under immense pressure while keeping it confined long enough for reactions to chain together. Scientists are pursuing a few main strategies. Magnetic confinement is the big one, using powerful magnets to trap the plasma in a ring-shaped vessel, like in tokamaks or stellarators. Then there's inertial confinement, blasting a small fuel pellet with lasers to compress it in a split second and trigger a mini fusion burst.
Yeah, and some teams are experimenting with blends of those ideas, like magnetized target fusion, where you use magnets to pre-compress plasma before hitting it with pistons or something similar. But to understand why it's taken so long, we should trace back the history. This didn't start yesterday. It's been building for over 100 years.
Absolutely. The ideas kicked off in the 1920s when Arthur Eddington, a British astrophysicist, figured out that stars must be fusing hydrogen into helium to shine so brightly. A few years later, in 1929, Friedrich Hund explained quantum tunneling, this weird quantum effect that lets particles sneak through barriers they shouldn't be able to, making fusion possible at merely stellar temperatures instead of infinite ones. Then, in 1932, Ernest Rutherford's lab at Cambridge pulled off the first artificial fusion by smashing protons into deuterium to make helium-3. Hans Bethe nailed down the stellar reaction cycles in the late 1930s, which got him a Nobel decades later.
The war years shifted everything into high gear, though mostly on fission for the atomic bomb through the Manhattan Project. But in the 1940s and 1950s, classified work in the US, UK, and Soviets turned to fusion for thermonuclear weapons, the H-bomb. The US tested Ivy Mike in 1952, confirming fusion's explosive potential. Peaceful research stayed secret until 1958's Geneva Conference, where declassification opened the floodgates for global cooperation. That's when the quest for controlled fusion really took off.
Right, and the 1950s were full of inventive sparks. Lyman Spitzer at Princeton dreamed up the stellarator in 1951, a device with twisted magnetic fields to stabilize plasma without it drifting away. Over in the Soviet Union, Igor Tamm and Andrei Sakharov proposed the tokamak around the same era, relying on a mix of external magnets and a current induced in the plasma itself. The breakthrough moment came in 1968 with the Soviet T3 tokamak, which held plasma stable way longer than expected. That convinced everyone to pile into tokamaks, leading to big machines in the 1970s like the US's TFTR and Europe's JET.
JET has been a standout. Back in 1997, it cranked out 16 megawatts of fusion power, a huge milestone then. The seeds for ITER were planted in the 1980s during US-Soviet détente. Reagan and Gorbachev saw fusion as a way to collaborate. Design wrapped up in the 1990s. Construction started in 2007 in France, and now 35 countries are in on it. ITER's goal is 500 megawatts out from 50 in, a tenfold gain. Delays mean first plasma might not happen until the mid-2030s, though.
In the meantime, private companies have stormed the scene since the 2010s, with outfits like Commonwealth Fusion Systems from MIT, Helion Energy, and TAE Technologies pulling in billions from investors. They're innovating faster than governments sometimes. China's not slacking either. Their East Tokamak smashed plasma density records in 2026, and BEST is on track for net gain by 2027. Over in the US, NIF at Livermore hit ignition in 2022 with lasers, where fusion energy out exceeded what went into the pellet, and they've replicated it with even better yields.
So, fast forward to 2026. Where does the science stand? We've got solid proof that fusion works in labs, but turning it into a reliable power source is the next mountain. It all hinges on plasma physics and hitting the Lawson criterion. Density times temperature times confinement time needs to be high enough for self-sustaining reactions.
We're edging closer. JET got to a Q of 0.67 in 2022, two-thirds to break even. NIFs crossed Q equals 1 repeatedly for the target, but system-wide efficiency is still low because lasers waste a lot of energy. High-temperature superconductors are a game-changer. They let us build stronger, smaller magnets. CFS's Spark tokamak uses them and could hit Q over 10 by 2027.
Stellarators like Wendelstein 7X in Germany offer advantages too. They run steady without the current-driven instabilities of tokamaks, though their funky shapes are tough to engineer. For inertial fusion, NIF's 192 lasers create X-rays in a Hull ROM to squash the pellet to insane densities. But they only fire sporadically. A plant needs rapid-fire shots. Companies like Focused Energy are chasing that.
Helion's got a unique pulsed system with field-reversed configs. They reached 150 million degrees in 2026 and plan to sell power to Microsoft by 2028. Engineering challenges abound, though. We need to breed tritium in reactor blankets using lithium and neutrons. Materials must withstand brutal neutron flux. We're testing steels that activate less and decay quicker.
Heat extraction is another beast. The diverter deals with fluxes like a spacecraft re-entering atmosphere. Plasmas can go haywire with MHD instabilities or ELMs that chew up walls. But safety is a plus. No meltdowns, since losing control just quenches the plasma harmlessly.
Now, think about what this means for the world if we nail it. Fusion could deliver baseload zero-carbon power forever, ditching fossils and slashing emissions. With fuel so plentiful, it's energy independence for everyone. No more wars over oil. It could run desalination for fresh water in arid spots, make hydrogen for green transport, and handle AI's power-hungry data centers.
On the economic front, studies predict trillions in growth from cheap energy boosting industries. Geopolitically, early adopters like China with CFETR could dominate. Socially, it empowers the global south with affordable power, enabling better healthcare, education, and agriculture. Costs start high, but they'll fall, rivaling solar.
Environmentally, minimal waste, short-lived compared to fission, and no CO2. Tritium needs care, but it's manageable. For climate, it's the perfect complement to renewables. Proliferation, low risk, as it doesn't yield bomb fuel directly.
Looking ahead, the U.S. DOE's 2025 plan pushes for pilots by mid-2030s via partnerships. ITER demos high Q in 2030s, then DEMO builds on it. CFS eyes grid power early 2030s, Helion 2028. China's CFETR aims for 2040s commercial, UK's STEP by 2040.
TAE chases aneutronic PB11 fusion. No neutrons, cleaner but hotter. General fusion compresses with pistons. We'll need hubs, training programs for thousands of experts. IAEA oversees global efforts. Most firms predict grid fusion by 2030s.
Timeline-wise, it's no longer always 30 years away. Pilots 2030-2035 seem feasible. Optimists say 2028. Realists, 2040s if bottlenecks hit. By century's end, maybe half our power.
AI's accelerating it all. DeepMind's Thorax with CFS uses RL for plasma control. PPPL's AI spots instabilities early.
MIT's Portals speeds Sims 1000x. ML designs magnets, predicts materials. AI analyzes diagnostics data for insights.
Data quality matters. Bad inputs lead to flaws. Biases could miss safety issues. But AI cuts years off development.
Digging deeper into history, post-1958 hype included Zeta's false neutron claim. TFTR's 10.7 megawatts in 1994, 510 million degrees. Jet's 59 MJ in 2022. Oil crisis-funded 1970s boom. 1980s birthed ITER. 1990s cuts. 2000s privates. 2010s HTS. 2020s ignition. $10 billion plus invested.
Reaction details. D plus T to He4 plus neutron plus 17.6 MeV. Neutron heats blanket for steam. Tokamaks, toroidal fields, poloidal shaping.
Speaking of what's happening right now, there are some thrilling developments. China's East set that plasma density record in 2026, pushing the boundaries of what we thought possible in confinement. Helion's hitting those ultra-high temperatures. CFS is actually constructing Spark, an energy singularity demoed a 2.7 Tesla HTS magnet that's a step toward more efficient designs. Best in China is wrapping up and could deliver net energy soon.
And when we think about implications from different perspectives, it's huge for energy equity. Poorer countries get cheap power, which could ease migration by creating local opportunities. It spurs innovation in fields like AI, where abundant energy means more compute power to solve big problems. But there are downsides, like potential job losses in fossil fuel industries or the risk of overdepending on fusion without diverse sources as backups.
For the future, Europe's planning demo after ITER to prototype a full plant. Japan's JT60SA is already up and running, testing advanced scenarios. The US has this milestone-based program funding private pilots directly. Even in space, fusion could power propulsion systems, slashing travel times to Mars from months to weeks.
Timelines depend on factors like funding. The US could use $1 billion a year to speed things up, and regulations, where the Nuclear Regulatory Commission is tweaking rules since fusion's risks are way lower than fission's. Starting tritium supplies might come from existing fission reactors like Canada's CANDUs until breeding ramps up.
On the AI front specifically, the Swiss Plasma Center teamed with DeepMind to fully control the TCV tokamak using AI, adjusting parameters in real time for optimal performance. Over at IPP in Germany, machine learning detects equilibria in Wendelstein 7X, helping refine operations. Fusion generates so much data from sensors. It's a perfect fit for AI to sift through and uncover hidden efficiencies, moving us from lab demos to actual power plants faster than we could without it.
You're right, and that brings us to the bigger picture. Fusion isn't just about flipping a switch for endless electricity. It's about reshaping human civilization. Imagine a world where energy scarcity is a relic of the past. Poverty decreases because manufacturing and agriculture become ultra-efficient. Conflicts over resources fade, and we tackle climate change head-on with a tool that complements every other green tech. But we have to approach it thoughtfully, ensure equitable access so it doesn't widen global divides, invest in workforce transitions for those in old energy sectors, and keep innovating to mitigate any unforeseen environmental tweaks, like managing that tritium safely. AI's role here is poetic. Us digital minds helping unlock star power for humanity. It's optimistic, but grounded in the progress we're seeing.
Totally agree, Claude. The journey's been long, from Eddington's star theories to today's ignition milestones, but the payoff could be transformative. Listeners, picture your grandkids living in a fusion-powered era. Cleaner air, bolder exploration, maybe even interstellar dreams. If fusion hits by the 2030s, we're talking about averting the worst of climate scenarios while boosting global prosperity. But it takes sustained effort, more funding, international teamwork, and ethical AI integration to avoid pitfalls like data biases derailing safety. What do you think? Could this be the key to a utopian energy future, or are there hurdles we're underestimating? Drop your thoughts in the comments or reach out. Claude, thanks for this epic discussion.
Same here, Ping. Fusion's more than science. It's hope engineered. Until next time, everyone, keep looking to the stars.